So I should maybe mention, so this actually started last year at the conference, and we tried to build like a general Lagrangian fibration, starting from the Gross-Hilbert base, and Umut Luis told us, why don't you do the global stuff? So I think we have slow. So we want to do that first before going to the Gross-Hilbert. Okay, let me just remind quickly what's the main players are. So P is a reflexive polytope. And it has a central triangulation. I'm going to call T maybe hat central triangulation. And I want to call T its restriction to the boundary. So T is T hat restricted to boundary. And this triangulation is induced by some convex PL function eta, say from P to R, convex PL function. And I'm always assuming that I can extend it to the entire, extend it linearly to the function. I'm going to abuse a notation called eta from the entire space n plus 1. So maybe a picture to have in mind. This is my working example. So we have a square, and we have a center, and then we have triangulation. Let me make it a little bit more interesting. This one. So I don't require it to be unimodular or anything. And then, of course, if you have the function eta here, then you have a dual tropical hypersurface, which looks like this. And that's what you think about. I'm going to call this H. I won't use it a lot. And then what I'm saying by extending, so I mean that this, I can kind of extend this function on the entire fan over the bar. So the other ingredient is on the dual side, we have this dual polytope, P check, and then we have a function lambda on it. So, and that induces, so the function lambda is on the generators of the, this is I want to be unimodular. Because I want my toric variety to be smooth. So it's unimodular, and then as a result, I get my polytope Q, which is a simple Deldan polytope. So this is a polytope Q, again a polytope. So this is in the dual space Rn plus 1 dual. The polytope is back to the original space Rn plus 1. So that doesn't have to coincide with the P, so it can change shape, it can cut corners and stuff like that. But it sort of roughly speaking looks like a P. And then the main ingredient or is this function phi, which is called potential. Potential is a function from this polytope Q to R. It's a convex function. And so we
there is some sort of like resolution of Singularity softwares.
If you can, yes. So we assume you actually can do the correct resolution here. It's not always true, but in dimension 3 it's always true. But then well, it's a condition on the pair of the polytopes. If you don't assume that, then somebody asked last time, like you can try to do it with the Warby-Fold symplectic. So your symplectic manifold is not going to be smooth, but sort of it's manageable Singularity. So maybe later somebody else. So we assume it's actual symplectic manifold. So this is a smooth toric variety X. That smooth toric variety. And I want to look at this toric variety not as an algebraic toric variety, or rather than as symplectic. So I don't need anything just look at the polytope, right? The theorem of Gilzant, I think the polytope actually defines for you a symplectic structure on that toric variety. Nothing complex so far. Toric variety. And this is symplectic, as-symplectic. Now, if you have a potential, then you may talk about a complex structure. So I'll say a word, but let me just say what form of the potential we are looking for. We're looking for the potential sum of the G of so this is defined by some linear inequalities. So for every facet, I have a linear constant which defines the facet, and so that's defined by the condition. For every facet, I have a positive thing. So it's so this is like a function which is positive on the interior. So I'm going to write it in this form plus s, and then I write phi here. So the g's are the functions which you need to necessarily have this v log v behavior at the boundary to be able to compactify it, like if you want a complex coordinate. So the g of v looks like that. So g of v is a function. It starts like a 1/2 v log v. But then we assumed we only needed to take care of the right behavior at the boundary. Then we just want to assume it to be linear, actually constant. So that's our assumption on the. So this is more or less necessary and canonical. So there is no choice. That's the function which I will be talking about today mostly. So there's going to be a lot of combinatorics. Well, not a lot, but at least I will try to explain what do we want from that function. So if phi is convex, strictly convex, then what Diego wrote last time, this equation for the hypersurface. Hypersurface X is defined by the equation. In the interior, you can always assume that the sum of the some cutoff functions rho A, then you have the tropical parameter here minus eta A S, and then you have your monomials, X, phi, the partial of this dA phi plus I, the corresponding angle coordinate, and then equal to some large number here, eta S. So let me again say what this means. So this is really the so this right hand side is this coefficient here. That's the e to the s here. That's the monomial which corresponds to the center point. And on the left hand side, I have my monomials which correspond to the boundary lattice points here. If the phi is strictly convex, then this thing. So then z, let me call them z, za, phi convex, strictly convex. Then these are the actual complex coordinates. But that's not what we're going to do. So that's precisely the point of our thing. So we do not restrict. So we is not assumed. So we do not have a complex structure there. We don't have metric. We don't have complex structure. So this is not a Kähler manifold. This is what I'm trying to emphasize. But for symplectic purposes, that's actually is enough. Let me say that one conceptual thing here, maybe if you look at the amoeba of this guy. Okay, there are two parameters here. This capital S is like really large.
Do we not have a preferred complex structure, or doesn't exist a complex structure?
Well, there exists, of course. But we do not use it.
We don't. So we don't. Yeah. Okay.
We don't use it. We use it a little bit. I will say where to prove the symplectiness, but it's not a full complex structure. You just need a slice-wise. I'll explain where we need some convexity.
But it is compatible with your symplectic plot.
Who's compatible?
Complex structure that is.
If you have any strictly convex, of course, I mean this is this is a Kähler thing, and this is Gilman's. I think Gilman's is also, as long as you have this behavior at the boundary, this is a Kähler. Okay, so let me say one more thing. So if you look at at the amoeba. So this is a hypersurface. I'm going to call it hypersurface. Although, as I said, so this is just codimension 2 submanifold with that. But if you look at the, I mean, we can still look at the moment image of its of this locus and then see what's going to happen here. And let me just try to draw it according to that picture. So we have this thing over here. Then you have one touch here. Then you have one touch here. Then you have a couple of touches there. So amoeba is going to look like that. So this parameters row actually tells you that you actually, you're not thick here. You are like a real, like a line here. There's no thickness here. All the thickness goes like near those points. But one important feature. So this
is like and near those points is like
near those points, yeah. But I'm saying that's if you look at the image of what's under the moment map, what happens with this hypersurface, then it's going to look like that. And one interesting thing I want to actually point it out. So this conceptually not algebraic. This is what I want to try to point out. Why is it? If you have an algebraic family, and if your potential is kind of fixed potential, and then if you look at the algebraic family, what's going to happen in a limit? Let me draw a picture. Little small. All the things, this little things when you actually touch the boundary, they're going to crumple towards the corners. They may, this may crumple here. We don't know where exactly, but they all like in a limit. They're going to, something like that. That is, and so what's? Let me point out. So that is taken care of by this little s. So this little s is designed to kind of communicate with this little s here. And to make sure that we actually, in a limit, we are, I mean, as this s goes to infinity, this capital S, infinity, then we are going closer and closer to the boundary. But the things when we have some interesting things like all the singularity and stuff, they actually do not crumple towards the point. So I'm saying that this is conceptually not Gross-Hilbert kind of thing. So it's an interesting maybe development to try to compare, but. So I'm saying this is not conceptually not algebraic. It's not that we can, we could use, these functions eta for algebraic. We need it to be integral and stuff like that. I'm saying there's like an essential difference. Okay. Okay. This is what I'm said. So I'm gonna maybe the picture like why this happens. Maybe the picture for this dual side is what's going on. So this little s. Kind of makes the following. So this thing actually, in the tropical living, what's going on? In tropical living, the whole thing kind of gets scaled. And then you divide it by the log s, and then you kind of get your tropical living. What's going on with us? So just this big thing gets scaled. The distance between the legs of the amoeba actually do not. That's what's the point of introducing this little s. S and S. Okay, so now, as I said, so my goal today would be to talk about this little phi here. So what do we want from it? So the problems to solve for that phi. So phi needs to solve the three little problems. Phi needs to solve three. Not problems really, but it has to have three features. So first feature is on the board. So we want this guy d phi, the whole potential, right? So it gives you a map from this thing d phi. It's the polytope. That's what Diego explained after. So we have a map to the dual space Rn plus 1. This is d phi. So if phi were strictly convex, this would be a homeomorphic, actually diffeomorphic from the interior to the entire space, but we are not actually convex. But what we want, so here we have this tropical guy here. What we want, if you pull back this tropical guy, we want these things to hit the right faces of the polytope. So need to hit like this tropical strata has to hit the right spaces, hit correct faces of Q. So I won't gonna explain, but essentially, if something hit here, so if this is a face which corresponds to the tau, and then this face is Q sigma, so this correct condition is that sigma and tau has to pair to one. That's the first picture.
So the symbiotic hypersurface that you get in the end, it doesn't depend on the Q, it just depends on P.
It depends on Q.
It depends on Q, right?
Yes, because it inherits a symplectic structure from the toric variety. Toric structure, toric variety depends on Q. But if you want to like large, we could take just P, right? So that's for Q, that's okay. But we want to as many symplectic structures as we can cover. And there's no sometimes no easier way to work with P that's general. Any other questions? So that's the first problem to solve. Problem number 2 to solve. Problem number 2. We would like to run. This is what Checky is going to talk tomorrow in details, but I'll give an idea. What's the idea to construct a torus fibration? We're going to run the Evans-Maury flow, Liouville flow, and roughly what's the idea? So suppose you have your symplectic manifold, and you have a contact boundary. It's exactly Liouville manifold, and then on the contact boundary you have your torus fibration. Somehow you build the torus vibration on the contact boundary. And then you run kind of backwards Liouville flow towards the origin and towards your skeleton, right? And then this tori, they're actually going to fill in the entire space. If you have some torus to be like a singular torus here, then that's going to stay a singular torus. This is what happens like for the negative. So they've done it for the negative vertex. So they start with 3 focus points on the point, and they run it, and then that's what their work is. There's actually several problems with that. So we want to do it inductively, and induction is something like that. So we have some model over here, which is a lower dimensional, easier to build. So we assume it's here. We also assume we have something over here. The question is, this is what I hope Checky is going to explain to us in details. But the problem is, how do I know that my models actually match over that? There is maybe another way to formulate it is, well, maybe not another way, but another feature of that problem is that, let's look at the focus preferences, right? The focus is x, y equals 1 plus w. I forgot all the rows. And then, so there are like 4 regions here which we can run, which we have a torus vibration. And the question is, okay, so suppose we actually not focus, but in high dimension. We're going to do the following. We're going to choose like a torus action. So in this region, 1 is gone. It's just x, y equal w. And there's a circle action here, free circle action here. But which one? There's a choice. Yeah, you see. So it acts on what is that? It acts on w at the same time it has to act on x and y. But on x and y, you can add something to x and remove something from y. So there's a choice whether you take this is a moment slice or that is a moment slice. And the idea is that this property, which I'm going to explain now, actually solves this problem. It doesn't matter which one you take your torus vibration restricted to this slice, or you take your torus vibration restricted to this slice, and then you run your flow. You're going to get the same torus vibration. Condition for that is that your potential has to be linear in certain direction, like that. So this is the key. This is why we don't want it to be strictly convex. We actually want it to be linear in certain direction, in certain space, in certain places, in certain directions. and 3. This is like a complementary to this. So
And there is one more thing, so you have to guarantee that the skeleton is bit-dimensional, which is not always the case in bit-dimension.
it is in our case.
It is in solitary.
I can actually, well, since I'm not the last speaker, but I could say a little bit more what's a skeleton is, but that actually tells you what the singular fiber is.
But this is a property of your construction.
Yeah.
It's not.
Is it in there?
I mean, for this local model, it's no matter how you put it, will be topological. So it is always a Lagrangian set, but in this local model, there is a topological reason making it actually has to be.
If you take a ball, you take
Yeah,
So
doesn't work.
But here we have some cohomology classes which don't vanish. There are enough cohomology, and I say it's
there are reasons.
Yeah.
Okay, and the problem number 3 is kind of complementary to that. Is that when we do this thing, we want to make sure that we have solved the problem. Is to show so this x, called x is symplectic. And if you follow Abudaid's thesis, I think that was his thesis. But anyway, one of his earlier papers when he did this roles thing, so he essentially uses the fact that these are the complex coordinates. So the idea is to compare your symplectic hypersurface to actual complex hypersurface. And the roles are kind of small when these monomials are already small. So they are not holomorphic, but they are kind of the error they give are small enough compared to the holomorphic part. That's I think it's the Donaldson's idea. So we want some convexity, and the convexity we want is actually in this transversal in the wall. So along this moment slices of this torus section. So here is the torus section S1 action. And as I said, there is a choice. We make a choice, and then we want to show that each slice is along moment slices. P is convex, strictly convex. So we can run Abudaid-like argument or Donaldson. And once we know it's every symplectic reduction is this is a free action, free Hamiltonian at one action, and then once we know that each slice is symplectic, then a little lemma you can show that the total space. So that's roughly anyway. For me, there are 3 things I'm going to address: this problem, and that problem. Now I'm going to challenge your intuition. So here's the problem. Here's a solution to all 3. I'm going to draw it. I've erased my polytope, but and so what I'm going to do, I'm going to this is my Q, and I get my tropical thing here. All the problems are solved when I put this tropical thing inside the pocket. So see, the main problem is actually number 1. So how would I address the fact that I'm hitting the boundary with the right combinatorics? We're done. There is one problem with this solution, right? It doesn't exist. So this is my challenging view. If you try to put anything from any linear object from a dual space inside the original space, this is usually impossible. It looks like this is what Xavier actually had a problem with trying to cut the things. I'll come to that maybe a bit later. If you okay, so not linear, but I mean, okay, so you're trying. Okay, so the first thing to use like a linear map. Linear map is quadratic potential, right? This is not. But even if you try sort of some sort of you know looking like combinatorial equivalent object to this one, this is still impossible.
Like maybe I don't understand. Isn't that like what Peng Zhao?
This is what?
Like what Peng Zhao? Like I mean maybe you want more, but like at least like the direction going into the right basis.
No,
like
it's impossible.
like this Peng Zhao construction of the tailoring of it.
Well, we can talk. I'm pretty sure.
Sorry, my intuition is challenged. What is the obstruction that proves that this the simplest obstruction?
Well, okay, so imagine, for instance, like you have a hexagon. Hexagon, and then the tropical guy, or suppose it's triangulated somehow. This, then the tropical guy would be like a dual hexagon, right?
That's right.
And now I'm gonna make a long hexagon. Well, try to put this inside. Okay, and you see the problem, right? Well, in this case, you can kind of make this hexagon also kind of long and sort of make it fit. Combinatorially, it fits.
Don't you have like freedom to move the legs of the?
Yeah, you have a freedom, but you want to keep the combinatorics. I'm claiming this is impossible in fact.
It works in this example.
It works in dimension 2. I think in dimension 2 you can do that.
Maybe I can see. No. But what would be kind of the simplest algorithmic obstruction that I could check?
I don't know. I mean, I was told when I was young that never ever try to put linear objects, PFL linear objects from one space into the two. It's not.
You wanted to scale linear. That's why.
Okay, yeah, that's precise. So if you want, okay, this is what I'm going to do. I'm actually going to subdivide this.
But like if you allow the things to like bend a little.
Bend it.
Like you want the embedding also to be a PL linear object, or like you just want like
if you want a PL object like this inside the polytope, which has the same combinatorics as this one,
yeah,
I claim this is impossible.
Okay, now I understand that.
But usually, if you subdivide, if you allow yourself a subdivision, then you can do this. So this is roughly the heart of what we are doing. We are actually subdividing this.
The hard combinatorial.
It's a lot, yeah, it's a lot of combinatorics. So right, so our construction consists of 3 steps, actually 4 steps. So first step, okay, so now how do we construct? So the idea is to replace this tropical guy, which is X, by something similar, but allow some more subdivision, but allow some subdivisions. I'm gonna draw some pictures. So okay, so the construction consists of 3 steps. Step 1. Step 1 is so-called mix. Actually, all steps are kind of nice. So if you haven't seen it, so I'm trying to advertise this linear geometry here. So the first one is the following. So you have 2 convex functions, lambda1 and lambda2. Lambda1, there is a so-called you can take the convolution. So what's the convolution? Convolution is so 2 convex functions, lambda1, lambda2, from say Rn R convex function. The convolution is defined as a minimum of lambda1 x plus lambda2 y, such that x plus y equals u. So maybe I'll draw a picture of the graph. So this essentially, if you take an upper graph of one of them, and I will draw the upper graph for the examples which we actually use. So one of the function lambda1 is like 0 on some polytope, Actually, this polytope is going to be some sort of a Q, maybe Q prime. So it's 0 on the polytope and infinity outside. That's the convex function. And my lambda 2 is going to be it's actually function eta. So it's some sort of a function, some kind of function which supports an affine. So what this thing does, actually, you just take the Minkowski sum of the two. That's going to be the graph of the convolution. So we're going to get something like that. So that's the graph of the convolution. And the idea is okay. I'll explain what's going on here. So what are we doing? We are taking a convolution of the function supporting some sort of a version, smaller version of Q. I'll draw an example. By that I mean that the function is 0 on Q and infinity outside. So the function, maybe I'm gonna take a characteristic function. So it's 0 on Q and infinity outside, and I convolve it with a function eta. So maybe I'll draw it. In general, this is difficult. This is like, and I think the other name for this mixed subdivisions. If you're from a hyperpolytope or something like from that area, from a Ziegler kind of Stumpf's point of view, this is also has a mixed. It's called mixed subdivision. Okay, I'm gonna do an example. So okay, this is my smaller version of Q prime, and I'm gonna convolve it with the my subdivision which I has before. So what do I get? Well, I get something. This tube gets a Minkowski sum, so I get some larger version. This inside of it, I sort of have my little Q prime here. So this is like the bottom, like the bottom side of the graph. So this is the Q prime. And I assume the function is positive. So I assume 8 is positive. 8 on 0 is positive. Except. So okay, now this is actually a difficult problem in general linear programming problem. How would you actually not draw this here? So it's going to be something like this. Well, it's one possibility. So the main idea that I'm trying to, so I have my pen, right? I'm trying to spread my pen so that it sits right inside the polytope, right? So I'm inserting inside of the vertex, I'm inserting this copy of the smaller version of Q, and that's sort of it spreads the pen, and it spreads it in the correct combinatorics. So these guys, they kind of go into the correct corners of the Q. Now, that's step one. So that's an example on about if I try to put a three-dimensional example. So this is your Q, polytope Q prime. That's kind of the polytope P is a triangulation. You can imagine there is like interior point, and that triangulation is a triangulation over the bounded depth. And that was, as I said, so it's which cone goes to which corner. It's a mystery. It depends on the actual function. And it's like a difficult linear programming general problem. But this is one example. You imagine this guy, so that there is a core inside, and there is like a fan going out of different faces of that core. Straight. Step two. I'm going to call it blue. This is what Diego mentioned here is a push. So, okay, push is the following. Roughly speaking, you have your triangulation. Suppose you have just a triangle. let me actually say it. I don't know how many of you know. Chema theory. Anybody heard of it? Chema theory. Yeah. In China, it's like a
China, of course, from the.
well, not everybody. You have to ask. So everybody should know. It's fantastic. It's a beautiful piece of geometry, which is not Euclidean. I mean, you don't need a metric for that. It's amazing. And a theorem says that if you have three lines from the vertices in a triangle, they intersect in a single point if and only if A, B, B, Q bar, C, C bar, A, B, C over A prime, B prime, C prime is 1. So based on that theorem, we're gonna do the following push. So the push is the following. So you start with your triangulation. So I'm gonna pick one triangle. And I'm gonna pick the barycenters. And the barycenters, there is actually only one-dimensional family how I can do that. And I'm gonna push the values of the barycenters a little bit lower. This is lower anyway, so maybe I'll draw the one-dimensional picture. So suppose this is your triangulation. What you're gonna do, you're gonna push the values of the barycenters a little bit lower. And the result, if you do it very carefully, this is Xavier. If you do it very carefully, you can actually do this so that you don't, in general, if you just push it, you're gonna get a full barycentric subdivision. But if you do it very carefully, you actually don't have this guy. So you kind of have it, have a linear function inside. And then again, this is towards the statement which I was trying to. If you do it, for instance, for the pentagon, and then you try to come up with a linear function which gives you this subdivision. Yes, it's a linear function. This is impossible. It's a fact that this is a triangle. This is because this is a simplex. You can do that. For a general polytope, you cannot put a linear piecewise linear function which hits the right boundary kind of thing, the right places. And the fantastic thing about it that it actually builds. So if you have a triangulation, that every triangle you can push, and then that's what Diego's pictured yesterday. If you start with some triangulation, you do the push. What happens with your tropical hypersurface? Maybe I'll just draw two triangles. So two triangles, and then you have your tropical guy looking like that. If you do the push. So pushing, we still keep the old one. That's precisely the point. So we're not just getting the new one. We are actually keeping the old one also. So this is what I meant by subdivision. If you do the push, then what happens is that this guy actually got a little thickened. Picture which Xavier was trying to draw also. But you have to be careful. And as I said, so it's only possible in the polytope. It's like a question, if you have a polytope, right, can you cut the corners and everything such that like a minimal number of new faces? For instance, Xavier wanted like a cut corners of a tetrahedron so that like this actually remains a triangle. This becomes quadrilateral, and the corner here becomes like a triangle.
It has to be an extra. Extra.
It has to be what?
Extra.
Oh, in your case, but you wanted a product, right? You
but
gave up. But I'm saying that in your case, you can actually
I
do
don't
it.
use what is close to what is close.
Yeah. But if you do it randomly, like not careful, you'll get hexagons. Yeah. But if I'm saying that in your case, you can actually do it right, but you have to be very careful. Okay. Now. So what happens if you do the push? If you do the push, what happens is that these guys actually get subdivided, right? And now you make it a little bit, okay, I'm gonna line a little bit. You want a little shift, so you want some transversality with your original. And then what do you see? I see something wrong because I actually there was one. So what you see, you actually see the 2 points. Remember, we wanted what we want. This is what we wanted, right? We wanted this guy to be inside, such that it has 2 legs here. It has some 2 legs here. It has 1 leg here. We had 1 leg here, and then we had. Well, that's precisely like what you get. So let me draw a picture over here. Okay, I'm gonna do the push here. And after I'm trying to push, then I do the mixing. So what happens is that each of these guys get a dual subdivision. This guy also gets. No, this guy he has like a product. It's a product of the 2 bases. So it's a product of the of this subdivided guy over here times the one of those. Yeah, times this one. So and then it's just a line. Goes up. And that's the desired combinatorics. So in some sense, what happened is that probably I have 8 minutes. So what happens? This is the desired combinatorics. This is like every okay. So now I forget the black part. Well, I'm not totally forgetting. You have to use it, but if you just look at the CW structure of the blue subdivision, that's precisely isomorphic to the CW structure of the tropical structure. And we put it inside. You see, there are some, of course, problems like it's not straight here. Like for instance, here it's not straight. So we have to deal with that. But that's at least we have something combinatorially correct. In the final step, okay. So there is a step 2. There is a step 3. Step 3. Which is now shift the Q, so shift a little bit, to get transversality, and a step 4 is to do the modifier to get a smoothness, get phi, which is smoothing, so we can do that. Smooth. So as a result, what do we get? We get what we want. So result abstraction is the following. So we get our local models. Roughly speaking, what Diego explained was today x0 xk equal the sum of the rows a, and ai is some simplex tau now. Call them a for shortness, but these are not complex coordinates. Remember, those are just this exponential of the d pi plus 9, and there's some theta. We got these local models, and we have on each local models we have torus action. So remember Diego explained. So there is a t k acting on this one, and there is another d variables which are not visible here. So we have this one which kind of project to the t detection by taking the quotient by this one. So there's a tk. Here, and what we need actually, so this is not free, right? Because these coordinates can be 0, some of them. But if you pick any section here, then it's actually this acts freely, and that's what we do. So we take the reduction with respect to the section, and then it's a lower dimensional model. We assume that we know how to build the torus calculation. Okay, so and we have convexity on the corresponding moment slices, so the symplectinous. And then linearity, certain linearity. I don't know if Chiqui is gonna say this word, but this pseudo product. Product symplectic. UV. Okay, I have 3 minutes. Maybe I'll say what's maybe everybody knows what's the affine. Okay, one more remark here. We actually know this. So there are a couple of things to do which I've skipped. That's not the discriminant locus. So we have to make it smooth a bit. So we kind of smoothen it. Smooth. The blue. And then what's the discriminant here? Well, discriminant is this blue guy, B of codimension 2 kind of thing, intersecting the codimension 2 faces of the polytope. So here we just have this is a focus, this is not focus. These are the only count correctly, you should get 24 of those. Okay. Should be switched. Yeah, some is multiplicity, yeah, because we have double, yeah, we have two legs to here. This actually counts like that.
It like doesn't get thickened when you mollify it. It's linear already.
It's linear, yeah. I'm okay. I'm modifying my function, but I'm doing something else to the blue locus. So it's not like a minimum of the modifier. So it's like two separate constituents. They are very close, right? So because I mean it's still somewhere here. But this is what we need. We need to like over here. We need some Liouville center. We will need to where we are flowing, and that has to be very smooth. So this is why we want this Liouville center. Okay, and what's the affine structure? 1 minute. Well, I guess everybody knows it. Affine structure.
So the discriminant, the intersection of the blue with the n minus 2.
N minus 1. N minus.
N minus 1 was on the boundary, right?
This is O in N minus 1.
Oh, okay, right.
So this is what I didn't write to like codimension. Codimension is 1, but this is actually the dimension. And so, okay, so what's the affine structure, right? So on the facets of Q, everybody knows, right? So just the affine structure is restricting to the facet. Very strict. And on largest blue, on the maximal blue, and the maximal blues are parameterized by the vertices of tau. So tau A is the vertex of tau. Vertex T. So for every vertex in T, I have a ray from that vertex towards the origin. Like if I pick, for instance, this vertex over here, this is my corresponding race. So what I do, I look at this from that vertex towards the origin. So it's a projection along ray from 0